Thank you. Today I'd like to talk about New Hampshire's experience with per and polyfluoroalkyl substances in our drinking water. For the remainder of the presentation, I'll refer to those substances as PFAS. But first of all, before I get into the talk, I just want to acknowledge that in New Hampshire's work on PFAS, we've had substantial assistance from EPA over the last couple years from numerous programs, both at the headquarter level and regional level, including Superfund drinking water, pre-remedial, their laboratories, and the Health and Ecological Division in the water portion of EPA. The objectives of the presentation today is to provide an overview of PFAS, the sources that we've seen in New Hampshire, how it occurs in the environment, and public health concerns. I want to describe our experience in investigating and identifying sources of PFAS in drinking water. And lastly, I want to end the talk on identifying areas where we need much more information and assistance to address this compound. I first of all want to give a sense of the magnitude of the issue that PFAS has been for New Hampshire. We've only really been rigorously assessing this for the last couple of years in the state, and already over $30 million in New Hampshire has been allocated for addressing PFAS at just a couple sites in New Hampshire. And we have much more work that we're going to be pursuing, as I'll describe later. Also, in our state, we have one groundwater contamination site where 30 to 40 square miles of 30 to 40 square mile area where groundwater has been impacted due to one site, and that's just unprecedented to have a plume that size. And we'll talk about that site a little bit more in a second. It's a big issue in that we're only in the initial stages of assessing for it, yet we've already had 3 significant water supply sources contaminated over the health advisory level that EPA has established and New Hampshire's groundwater standard. And just since March of last year, in response to the discovery of some new sites, we have sampled over 2,000 sources of drinking water for PFAS. And from those results, we've already put over 600 homes on bottled water to replace their private well supply for drinking water as a short-term measure. And we've already initiated a substantial project to extend over 20 miles of pipes to about 500 homes with private wells that have been impacted by this contaminant. Again, all this just from about a year ago. This is just not another contaminant du jour of the day. PFAS is going to be something that we're going to be dealing with for quite a while. And it's also quite different than other contaminants that we've dealt with and other emerging contaminants. First of all, in New Hampshire, we have 2 sites where groundwater has been contaminated over a broad area due to air emissions. And this just blows up our traditional waste site investigation source water protection approach to work, where you look at contributing area for drinking water sources, be it groundwater, surface water. You look at land uses and make sure that historical activities and current activities are suitable for the protection of groundwater. In the case of an air emission, you can have a release occur in another watershed, another aquifer, over a mile away and impact a source. And also for site investigation, no longer do you have that point of discharge and where you trace the plume out from there. In this case, we have air deposition. The wind blows every which way, and so you are chasing contamination up gradient, cross gradient, and cross surface water divides. It just really complicates the issue. Another big issue with PFAS is that unlike most other contaminants, especially man-made contaminants, this contaminant is detectable in our residents' blood. So in this case, you see an effect of drinking this contaminant in water. While there isn't a health index to really interpret that information to say how much PFAS in your blood is too much before you have an adverse health effect, you do see the cause and effect, and it really captures the public attention when they see they have higher than average levels of PFAS in their blood due to their drinking water. Another issue with PFAS is that right now there's only health advisory levels at the federal level, and then in New Hampshire standards for just 2 of thousands of PFAS compounds, and there are thousands of PFAS compounds. Labs can look up for about a couple dozen of these compounds right now, but Current literature, including articles just this month, document that there's potentially thousands of these compounds. Another big thing about PFAS is that short-term exposure for susceptible populations, being an infant or lactating woman, is considered a health risk. So it's not one of those health guidelines that's based on drinking water for decades and a lot of water for decades, that you might have an increased chance of having an adverse health outcome. Instead, this health advisory level issued by EPA has some pretty clear language that it's a do not drink advisory for susceptible populations. So that's pretty stringent health advisory level. It's to say people should not drink this water, period, if it's over the standard health advisory level, which we'll talk about those numbers in a second. In our state, people that have been exposed to PFAS in their drinking water are so alarmed by what they have found on the internet about its potential health effects, by the fact that it can be seen in their blood or their family's blood at elevated levels, that they are demanding zero, whatever zero means. And I know that's a nonsensical concept to some degree, but that's what the public's demanding. Something else is to consider is that while EPA has set a health advisory level, and New Hampshire has incorporated that level as a drinking water standard, there are other states looking at standards that are 3 to 5 times lower than EPA's recommended concentration. Just to give a real quick introduction to PFAS, basically it's a large family of synthetic organic compounds that contain multiple fluorine atoms. The two most studied are perfluorooctanoic acid, or PFOA, which is how, or PFOA, which is how I refer to that the rest of this presentation, or perfluorooctane sulfonate, which we'll refer to as PFAS. Again, it's a family of thousands of diverse compounds. And these chemicals have been used so broadly that they're somewhat ubiquitous due to not only their broad use, but that fact that they're very persistent. They're designed by their nature to not break down, and they have high mobility. They're a concern because of known or suspected toxicity, especially for PFAS and PFOA, which we have a lot more information on than the other PFAS compounds. They bioaccumulate in people that consume the water, or in organisms that consume the water. And they can have very long half-lives, so they can, a half-life, it varies based on the carbon chain of the PFAS, but it can vary from months to 8 or so years. Information is rapidly evolving on this topic. I'm now going to go through a few slides that just show some of the general sources of PFAS. The list is very long, and there's a lot of questions that we're still pursuing. But PFAS have been used in a wide variety of industries and commercial products, such as bioresistant compounds, dust suppression, oil, stain, grease, and water repellents. And on this slide, you have a picture of Class B or AFFF firefighting foam that's used to fight hydrocarbon fires. So if you have a tanker rollover with a fire risk, a car fire, an airplane crash, fire departments will use something called a Class B foam to fight that hydrocarbon fire, which is different than Class A foam, which they use for non-hydrocarbon fires, and it's more typical type of foam that you'll see the fire departments using unless they have this special type of fire. Other uses are things that we have in our house, such as food surfaces, Teflon pans, pizza boxes, popcorn bags, food wrappers. PFAS makes a great surface so that grease can't penetrate paper or cardboard. And this is just not an historic use of PFAS. A recent publication you'll see in the second footnote here by Laurel Shader of Silent Spring documents that you still detect elevated levels of PFAS in food wrappers, including PFOA and PFAS, which have been phased out over time. And so these compounds continue to be used today, and other literature that preceded her recent studies shown when used in food wrappers, it can impact PFAS levels in food that we consume. Other uses include polishes, waxes, and paints, stain repellents, and cleaning products. And then electronics manufacturing, oil and mining for enhanced recovery, fluids that they use with that processes, and in certain fuels and hydraulic fluids that's been used. We also have seen PFAS as coming from leachate in landfills and detectable in groundwater and monitoreable near landfills, and I'll share some of that data with you. In New Hampshire, we've yet to assess this. We're about to assess this, but in other parts of the country, we've seen where elevated levels of PFAS occur both in surface and groundwater near biosolid application sites. And then, of course, as I mentioned before, when there's fires and crashes and things like that, and foams have been used, we've seen it at Air Force sites and airplane crash sites and car crash sites, and in firefighting training areas is another big area that has also been detected. Here's a diagram that shows sort of the occurrence of PFAS compounds in the environment from industrial uses to our own domestic uses. And so it shows the sources, it shows how they cycle through the environment, and then what the point I really want to get across here is how it can be recycled back as it comes from its original source into the environment, into water, and then from water back into either biosolids or drinking water and gets reintroduced. So there is a cycle and recycling of PFAS in our environment. Human exposure pathway is a few different mechanisms. One is diet, especially from fish and seafood and produce, drinking water, of course, and then incidental soil and dust ingestion. Generally, the consensus is that minor exposure pathways include dermal absorption and inhalation, although I have heard some disagreement among experts about really the quantification potentially for the exposure to inhalation, and that might warrant to be elevated closer to the major category, but the consensus seems to be that it's less of an issue. For the two PFAS compounds that we regulate, PFOA and PFAS, exposure is decreasing, and that's due to the fact that in 2006 that manufacturers in America joined an EPA global stewardship program and agreed to phase out the use of PFOA and PFAS by 2015. The shortcomings of the approach right now, though, is that we really don't have a process to ban PFOA and PFAS from materials that are imported. And then also we're learning that PFAS chemistry is complex, and even though manufacturers are adhering to this agreement and not putting PFOA and PFAS as ingredients into their products, it somehow comes out the end of the pipe or in emissions at the end of the process. And so there's still some generation of these compounds in America, although it's been significantly reduced due to this stewardship program and the agreed phase out of these compounds. Another thing to point out is that PFOA and PFAS are being replaced by other PFAS compounds with no health information. Generally shorter chain compounds where they're thought to not persist as long as either in our bodies or in the environment, but there's really no toxicity information to really speak to the health risks associated with these compounds. And so the same things that cause the PFOA and PFAS contamination that I'm going to talk about in a little bit are occurring with different PFAS compounds that are being also now discharged to the environment. Just speak a little bit about toxicity, the toxicity of these compounds. I'm a hydrogeologist. This is not my areas of expertise, but basically health studies for PFOA and PFAS have identified non-cancer health effects and potential carcinogenic effects. In this case, the non-cancer effects produces a lower health advisory number and was the key value for determining EPA's public health advisory level. And the toxicology is complex. There's a lot of studies out there, especially on PFOA and PFAS. There's many studies that find a correlation with possible adverse health effects based on lab research, but then sometimes other studies find contradictory results. And so it's somewhat unsettled at this point, but there is enough information that available at EPA felt like there was enough information available to develop public health advisory levels for PFOA and PFAS. And in New Hampshire, our environmental health specialists reviewed that information and agreed, and we adopted a standard. As I mentioned before, there's other PFAS compounds. In New Hampshire, we're looking for about 24 compounds when we sample, and on the slide you'll see a list of other PFAS compounds that we've detected, but that we have no health message for right now. We have no basis for making a standard in New Hampshire, nor, other than sharing with the public the results, can we characterize the health threat associated with the occurrence of these other PFAS compounds. The point of this slide is to just show that, based on the length of the chain of the PFAS compound, it's more likely to bioaccumulate longer in your body. The shorter chain compounds persist in your body for a lower period of time, and it's also thought to be the same in the environment, that the lower chain compounds would break down more readily than the longer chain compounds. And that when it does bioaccumulate, it's partitioning to protein, not fat, so it tends to be stored in your blood, liver, kidney, and muscle. Last year in May, EPA developed a public health advisory level for PFOA and PFAS. When combined, you add them up, and if it's over 70 parts per trillion, you exceeded EPA's new public health advisory level of 70 parts per trillion. And as I mentioned before, New Hampshire adopted that as a drinking water standard. Up until last May, we were operating on guidance from 2009, where there were separate health advisory levels for PFOA of 400 and 200 parts per trillion. I'll just point out that public health advisories issued by EPA are not enforceable drinking water standards under the Federal Safe Drinking Water Act. It's just EPA providing health information so that states can then use and incorporate into their programs as they see fit. EPA has done sort of this alternative guidance approach for drinking water, contaminants that might be in your drinking water for many years now, where in some cases there's screening levels, sometimes there's reference levels, or there's public health advisory levels for a broad variety of contaminants, including man-made industrial contaminants. And it's helpful because the last industrial man-made contaminant, maximum contaminant level established by EPA under the Safe Drinking Water Act was back in 1995, and seeing that process hasn't generated a lot of information for these emerging contaminants, it's very useful to have at least the best available information from EPA on these compounds, so that at a state level we can take appropriate action if we find these compounds in our drinking water. I'll just point out some other regulatory standards in New Hampshire. We have ambient air limits based on inhalation exposure. This standard is in no way protective of groundwater quality. It was never intended to be. It's something we are looking at our legislature right now, trying to assess if we can change our air quality laws to ensure discharges to airs are also protective of groundwater quality. We have soil guidance in New Hampshire for direct contact. We had to develop these values due to some sites near schools and playgrounds and ball fields. Again, these levels are direct contact and are in no way protective of groundwater quality or speak to the suitability of using these soils for growing vegetables. We do not have a surface water standard at this time relative to protecting aquatic organisms or fish consumption by humans, but it's something that is being discussed because we do have some surface water bodies in the state impacted with PFAS contamination. Now I'm just going to give a brief summary of our investigation in New Hampshire into the occurrence of PFAS. We have a lot more information on Department of Environmental Services website. It's really easy to find if you go to our homepage. It's the biggest thing you see on our homepage, a link to our data on PFAS. But just quickly, here's a list of specific sites where we've been sampling drinking water wells around, the first two sites being the air emission sites and areas with a large number of private wells. And you can see the concentration, the distribution of results based on concentration in the columns at the top of the table. As you go down through the table, you'll see a number of landfills as indicated by the LF letters after the initial name, And then we have some other sites such as fire stations or a former Air Force base, and then just general investigations where we looked at things like car washes or waste-to-energy facilities and places like that. This is just a condensed version of that table, summarizing results, again with the first two sites being area emission sites, and then categorizing the results by fire training areas. And then the bottom row being an interesting one, where this topic has gotten so much interest in New Hampshire that a number of homeowners have sampled their wells and they paid for the costs themselves, and then they shared the results with us. And we have a couple instances where we had isolated neighborhoods with clusters of private wells with elevated detections of PFAS compounds. Now I'm going to just walk through two of our sites quickly. This first site is a Saint-Gobain facility. It manufactures textiles coated with PFAS compounds. The materials are used often by the military to protect equipment in the field or from exposure to chemical agents. And what this facility did, and you can see the building on the top right-hand corner there, is that they coated these fabrics with compounds, and then as they dried the fabrics, they had these 50 horsepower motors that powered blowers that blew air out of the stacks on top of the building, and what it discharged were these real small particles that you couldn't see as it was discharging, but these particles flew up in the air and settled on the ground, and then as it rained, it dissolved these particles into the ground. And what you see on this map are a bunch of dots, which are private wells for homes in the area, and where you see a red or purple dot, you see that water from that private well was above New Hampshire's standard of 70 parts per trillion. So in this case, we have hundreds of wells that are contaminated, and where we have wells that aren't impacted, surrounded by, or aren't contaminated over 70 parts per trillion, surrounded by wells that are over 70 parts per trillion, we have to assume that they are very susceptible to the contamination, and so they're also being treated as if they're contaminated just because they're encircled by other wells with groundwater results that are over our health standard. The circle on this map is 1.5 mile radius, so we're well beyond that in detecting the contamination, and so that's where we get to the 30-40 square miles of area being impacted. The large area on the left hand of the slide where you don't see dots and you kind of see a gray hatch with the roads there, those are neighborhoods on a public water system, and so that, in New Hampshire, public water systems sort of start and stop somewhat unpredictably. It's often based on development trends, geology, density of development, and so you have a mixed situation here where we have water systems in the area and then whole neighborhoods on private wells. Luckily, we have public water in the area, so we're doing major projects to extend public water supply to all these homes unless the homeowner forbids that connection from occurring. And here's just a cartoon showing sort of the release mechanism for this facility, where you had the emissions, you had the wind transport, the settling on the ground, and then the recharge of the precipitation to the groundwater and the contamination of groundwater. And what even complicates things more here is that these homes are also in septic systems, and so they, the well types in this area are all different. They're shallow, overburden wells, deep bedrock wells, somewhere in between. And so you have the water being withdrawn from the well, being used in the home, and then discharged to septic. And so you had the redistribution of the PFAS contamination after it was initially released based on its water use in the area. A second site I'm going to walk through is a much smaller site. It's a fire department in Kingston, New Hampshire. You can see that it's well right there on the concrete cover in the slide. And on the left-hand side of the building is a faucet, and the Northeast has been in a significant drought, one of the most significant droughts in decades. And so we had a large number of private wells going dry, and as an emergency response, the state was asking towns to make a local source of water available to the public in case their well went dry and they weren't able to replace that well for a few weeks due to backlog of well drillers during the drought. And because this fire station was not a regulated water system and they wanted to make it available, the state went out and tested it for traditional contaminants, things that you normally regulate for drinking water. And then we also sampled it for PFAS because it was a fire station. And we had limited information about the potential to find contamination, but we know most fire departments stored this material on site. And in this case, there's no sewer in the area. It's all septic tank or septic systems. And so we tested this well, and we found it to be contaminated at 140 parts per trillion combined for PFOA and PFAS. And then we found, as you see in this map here, these dots are the private residential wells. You'll see we had elevated levels of PFAS in the neighborhood, including 3 other exceedances of drinking water wells. The interesting thing about this site, and it's not shown on this map, is beyond PFOA and PFAS, we had hundreds of parts per trillion of unregulated PFAS compounds. And so when we conveyed the results to the homeowner, we had to say, well, you meet drinking water standards, but we detected all this other stuff at these levels, and we don't have any health information for you. So it presented a situation where it was a little uncomfortable telling people there were PFAS compounds over hundreds of parts per trillion in their water, but there's no message and no mitigation measure being offered to them for that. Something else we've done in New Hampshire is we've reached out to all of our community water systems and then our non-transient water systems, the water systems such as like schools or office buildings, and the same people drink the same water every day basically. And we sent them all letters and follow-up emails asking them to voluntarily sample their sources for PFAS compounds and to share that data with the department. And from that voluntary request, we have about 400 sources of water that have been sampled, and we had about 62% of those show non-detect results, and generally low reporting limits were utilized, but the water systems didn't always follow our analytical advice. Sometimes lower reporting limits were not utilized. We had 26% detect PFAS or PFOA and PFAS less than 10 parts per trillion combined. We had 6% detect between 10 and 20 parts per trillion for PFOA and PFAS, and then we had 6% detect over 20 parts per trillion for PFOA and PFAS. I want to point out that these sources were in areas that we didn't necessarily expect to be contaminated. We have a whole other set of water system sampling results near suspected or known PFAS sources that would change these statistics on occurrence quite a bit, but I didn't want to skew the results by our targeted sampling near some industries, so this is just general statewide volunteer sampling. I'll also point out that if I redid those statistics that I just provided to include all the PFAS compounds that we're looking for, just not PFOA and PFAS, we would see an increase in the number of detections. And then if we filtered out the lab data where water systems didn't follow our analytical advice and they used higher reporting limits, we were asking them to use a reporting limit of 5 parts per trillion or less, but some use labs with 20 and 40 parts per trillion reporting limits. We'd also have a higher percentage of detection because we have a lot of less than 40 parts per trillion results that isn't really instructive for the statistics above. Kind of an interesting note, we had a number of schools and healthcare facilities or institutions voluntarily sample and share data with us. And from that data, we saw a relatively high level of detection, frequency of detection for schools, healthcare facilities, and institutions that have their own well, their own septic system. And while we haven't gone out and done an inventory of all the historic uses of those properties or the chemicals on site, our hypothesis is these are the places that clean their floors every day. Schools at the end of every day clean every floor and mop it and have wastewater from that process. And the only place these entities have to discharge their cleaning fluids is into their either out back on the ground or down the drain, which would go to their septic. And there is good information from EPA and there's a link to the report. I think it's from 2009 that does show high levels of PFAS compounds in different floor cleaners and strippers and waxing agents. And so it's just an idea that might be why we're seeing it at these type of entities more so than other entities that don't clean as much. Another area where we look for PFAS contamination is at car washes. Some of our staff observed as they were getting their car washed that there's a Teflon blinking sign as you go through the machine as you can sit in your car. And while we didn't know what that really meant, we do have a number of car washes not near a sewer, and so they have groundwater discharge permits. And when you look into it, the manufacturer of the cleaning agents for these cars advertise right on their website a Teflon formulation. Teflon's a pretty broad product line that can mean many different PFAS compounds. It doesn't necessarily mean PFOA or PFAS. So we did sample groundwater at some of our car washes, and we did detect elevated levels in PFAS in one of the car washes that advertised using the product I just showed you. For PFOA and PFAS, it's combined. It's below our 70 parts per trillion, but it is elevated. It's over 50 parts per trillion. But what was really interesting is the unregulated PFAS compounds showed up at over 9,000 parts per trillion in the groundwater. This happened to be a monitoring well, not a drinking water well, but it was a groundwater sample. And so just an example of other possible sources of these compounds in the environment. We also sampled some municipal wastewater. This wastewater system happened to have a very long pipeline to get to a big river to discharge its treated wastewater, and the pipeline went through a area we had a PFAS plume, and so we had to assess if it was a possible source for that plume, and we determined it was not based on the concentrations that we had in the plume versus what we see in this discharge, at least based on current discharge data. But what you see here is the influent concentrations of PFAS, and then the effluent, which is after it's been treated and it's homogenized in some very large lagoons, and then at the outfall, and that's again a water sample from the lagoons at the end of the several mile long pipeline before it's discharged to the river. And you can see that there's elevated levels of PFAS in the wastewater, both the untreated and the treated wastewater, including the PFOA and PFAS, which are phased out at this point. This could have possible implications because in a number of areas in the country, municipalities or small developments can't discharge their wastewater to a wastewater plant that discharges to a river, so they have to permit groundwater discharges, and it could be in an area where there's also drinking water wells nearby, and so the typical wastewater treatment process does not remove PFAS compounds, and it would be very hard at this point to change that treatment process to remove PFAS compounds. It's also concerned where wastewater is being used to recharge aquifers, which is a really popular sustainable activity for protecting water quantity. But typical wastewater treatment processes wouldn't remove these PFAS compounds, and so we have to assess what levels of PFAS are going to be in wastewater and make sure we're not contaminating the environment or drinking water resources by recharging the wastewater. And similarly, wastewater reuse, something that's even popular in New Hampshire, using highly treated wastewater for snowmaking, for golf courses. We have to make sure that as that's being sprayed all over the place from the wastewater plant, that we're not spreading contamination. So the fact that it's in wastewater will pose challenges, especially if more health advisory levels are developed for the other PFAS compounds. We have a number of future considerations, things that we're going to be pursuing over the next year, and a lot of this work is ongoing right now. We're looking at other potential sources of PFAS in the state in close proximity to private or public drinking water wells. In some cases, we're asking for more information, conducting inspections, or even going out and sampling wells or materials that are used at the facility. We're combing our internal files, using our GIS system, which is really good in New Hampshire, to try identifying other places where PFAS have been used, and see if there's drinking water sources nearby and sample those if they are. We're targeting public water systems near high-risk activities, so near firefighting training areas, near areas of known fires, near industries that may have used PFAS currently or in the past. We're with our own resources going out and sampling those public water systems. We are about to start assessing groundwater near land application sites. The literature in other parts of the country show that this activity could impact groundwater. We have to see if it's an issue in New Hampshire based on our regulations for the amount of biosolids that can be applied and the types of industries that might be associated with the wastewater plants that generate those biosolids. So we will be sampling drinking water wells near these sites, as well as sludge at a number of plants that provide their sludge to generate biosolids. Another thing that New Hampshire has done is that we have integrated PFAS sampling into our waste site investigation process. So we have about 800 active waste sites in the state, and that could be anywhere from a landfill to a former hazardous waste site to a site where it's a permitted groundwater discharge. And we sent letters to all those entities telling them that they need to integrate PFAS sampling into their routine groundwater monitoring that's occurring for other contaminants. And there's a link that provides that letter that we sent out to those sites. I already talked about the voluntary public water sampling request. Another initiative that's going to start in about a week, we've already laid the groundwork in meeting with state and local fire officials to talk about this effort to make sure we get it right, but now we're ready to launch this effort. We're sending out a letter to fire departments, municipal health officers, and town administrators, letting them know about the potential for Class B firefighting foam, or AFFF, for the potential for it to contaminate groundwater, and ask them a few things: to report to us where they've used this material in training or in fighting fires historically, so that we can assess if there's wells nearby that should be sampled. We also are establishing a reporting process where if they do use these materials, and we encourage them to use them appropriately, because you need to protect life and structures and property, but if they do use it, to let us know right away, so that one, we can assess if we should get out and do some initial immediate remedial measures to contain the spread of the possible spread of the contamination, and to again sample wells nearby, both right after the event and then at an appropriate time in the future, to ensure people aren't being exposed to this to contamination. There's a lot of analytical issues to deal with PFAS. First of all is what method do you use? What reporting limit do you shoot for? What list of analytes do you look for? Do you look for what only you regulate, or do you look for all the potential PFAS compounds that a lab can identify right now? It might cost a little bit more, but you get a lot more information. The traditional analytical method that's out there is EPA method 537, that was developed prior to 2010 to support the Unregulated Contaminant Monitoring Rule Round 3, or UCMR. And there's a number of labs in the country that were certified by EPA to complete this analysis for that sampling event, which required that any public water system serving more than 10,000 people sample for 6 PFAS compounds, and then a whole other array of unregulated contaminants as part of a routine sampling requirement that EPA administers every 5 years for unregulated compounds. So there are a fair number of labs that offer method 537. The method itself covers 14 compounds. In practice, most commercial labs only are reporting 6 of the compounds, and those are the 6 associated with the UCMR. There's a more modern analytical option that most of the large commercial labs are offering, and what seems to be most researchers and labs believe is a gold plate standard, and that's analyzing PFAS through isotope dilution, which can look for over 20 compounds, have lower reporting limits. The shortcoming of the method is that there isn't a standard method to reference at this time. Excuse me. And that each lab has kind of developed their own in-house method that has different holding times, uses different preservatives, different bottle types. And so it's really calling for some standardization or a requirement that each lab get its method accredited by an appropriate national association. Another issue is because you're looking for these emerging contaminants, using differing methods, going down to the part per trillion level, and now we're regulating at part per trillion level, so we're making decisions at a really low level. The question is, does data compare well from lab to lab? And sometimes it does, and sometimes it doesn't. A recent issue that was addressed by EPA in September of last year is that it was determined that labs were interpreting method 537 differently. None of them were doing anything wrong. They were following the method, but the method was vague on how to handle branched and linear isomers for PFOA. It addressed linear and branched isomers for PFAS, but not for PFOA. And so some labs were looking for the branched isomer of PFOA, and some were not when they were reporting the results. Just point out, given all these issues above, DES does recommend lower reporting limits and using an extended list of analytes when we're doing sampling in the state. And the letter I referred to before from our waste division asking sites to sample list of compounds and reporting limits. We don't believe constraining the lab results is wise. It might make a cleaner data set to only have results for things we have standards for and to only have detections of something that's closer to our standard. But this is an emerging issue. There's more and more information being generated, and should we have new information about the need to change our health standards or standards for other PFAS compounds, it would be good to have spent just a little bit more money to get the most complete data. So this map this slide just summarizes the branched and linear isomer issue for PFOA. And basically what you see in the bottom right-hand corner is a chromatograph, and where some labs were integrating both humps there into the results, the branched and linear form of PFOA, and others were just going with the linear isomer. And so that was addressed by EPA in a technical bulletin in September. DES, working with EPA Region 1, documented this issue, and we were able to finally tease it out after doing some proficiency testing with the labs and then doing split sampling among 3 different labs and seeing who was the outlier and then doing some analysis of how they got to the result versus how the other labs got to their results. There's another known issue with labs. We were working with one lab who does a really good job, but tends to be consistently low for certain waste sites when compared to labs that are also analyzing samples from those waste sites. And what we found in working with them, and they did this work on their own, is that they bought certified standards from 2 different companies and created calibration curves and then analyzed the samples that we submitted. So that would be sample 1 through 7 would be private wells that we sampled. And what you see is that based on what standard they purchased from different companies and again certified standards, that they got results that differed by 20 to 30%. So that's kind of scary that right out of the gates, the lab, before they even have any, before they even start work and possibly have any errors occurring within their work, that they're working with products that could be 20 to 30% different than products other labs are using, even though they paid for the certified standard. So it just shows that some more work needs to be done. While 20 to 30% is a pretty good, probably error bar when you're looking down to 70 parts per trillion, if you have levels of PFOA and PFAS in the environment that are around 60, 50 parts per trillion with one lab and over 70 parts per trillion with another lab, that can lead to big consequences for enforcement relative to requiring water treatment plants or cleanup and site investigations. So it is a big issue. I'm going to go over just a few slides summarizing work in New Hampshire that has occurred to test the levels of PFAS in human blood samples. And in New Hampshire, our health officials, which are in a different agency, they did not recommend that broad blood sampling initiatives be undertaken in the state. And they felt that way, not that they're uninterested, is that a health professional only recommends tests when they know what to do with the result, and there is no information that tells a person or a doctor how to respond to a concentration of PFAS in blood, and so they were hesitant to support it. However, the public worked with elected officials at the state and federal level to get these projects initiated, and we've now had thousands of people in the state had their blood sample for PFAS compounds, and it's been at different types of sites. It has been at a PFAS site, where firefighting training occurred at a former Air Force base or airplane crashes occurred, and then it's been at sites where PFOA has been the main contaminant, such as southern New Hampshire, the St. Gobain site. And so what you see on this map is a summary of results for PFOA, PFAS, and PFHXS for our different sites. Southern New Hampshire, as indicated, being a PFOA site, Pease being an Air Force base, being a PFOA and PFAS site, but PFAS being much higher, and we had 2 sampling rounds over the last couple of years. And then what you see is the general U.S. population. CDC does maintain a national survey that has looked for PFAS compounds in human blood throughout the country. And so you can see for PFAS that southern New Hampshire, which was a PFOA site, is lower than the average citizen in America, where there's no known special source of PFAS nearby, but that people that drank water from wells at the former Air Force Base, they do have relatively high levels of PFAS when compared to the average U.S. citizen. The middle set of bars shows results for PFOA, which, the blue bar being southern New Hampshire, again, being exposed to the air emissions at St. Gobain. They have much higher levels of PFOA in their blood when compared to the average population of the United States. And then the last set of bars shows results for PFHXS, which we don't have a health standard or advisory for at this time. But you also see for Peas that there was relatively higher levels of this compound in human blood when compared to the average U.S. population. This chart shows the average levels of PFAS level in blood for different sites throughout the United States. It includes industrial exposure scenarios, such as the 3M workers on the top of the bar. And so this is PFAS, so in this case you expect Pease Tradeport, the former Air Force Base, to have relatively high levels. And you can see it does. The 2016 and 2015 levels are higher than the U.S. population in 2011, 2012. But the interesting thing here is if you look right above, the average U.S. population in 2005, 2006 have higher levels than the people at Pease do right now. And so this was before the manufacturers phased this out, PFOA and PFAS out in America. And so at one time, we all likely had higher levels of these compounds in our blood, even higher than what people drinking contaminated water at Pease had at this point in time. So it just showed how ubiquitous and how pervasive the use of these compounds were nationally. This shows the average levels of PFOA. So in this case, you expect southern New Hampshire to be higher than the average U.S. citizen, and that's the case here. And then Pease, which had PFOA but not at the elevated levels we had in southern New Hampshire, is also lower. But as with PFAS, you can see that although you see a relatively higher level of this compound in people's blood in areas where they were exposed to it in their drinking water, they go nowhere near the levels in people's blood in other parts of the country where there were more industries or the industrial exposure scenarios, such as the 3M workers. So I just want to close by going through some information needs, things that we have identified that is needed as we pursue work on this. And first of all, and I mentioned it before, is getting more guidance on health effects associated with other PFAS compounds other than just PFOA and PFAS. And then to keep reviewing and reevaluating health guidance on PFOA and PFAS to make sure we have appropriate values in place. The science continues to be ongoing, and we need to be able to react to it and amend our regulations upward or downward as the science dictates. Another area where we need to do more is to make sure the Clean Air Act works seamlessly with both the Clean Water Act and Safe Drinking Water Act to be protective of groundwater. Beyond our examples of these compounds in New Hampshire, is there anything else that we're missing? Is there any other emerging contaminants that we should be looking for so that could have been released via air emissions? And then what about the emissions that are ongoing right now, even in New Hampshire at the sites that I showed before, that are now emitting other PFAS that we don't regulate? They're thought to not persist as long as they're shorter chain, but they are still they're still producing the same type of products, just using compounds that we don't regulate. So does that make sense, or should be something be done to address this class of compounds? And then lastly, when you're looking at an air emission, it's probably impractical to get to zero on, whatever zero means, for even the PFOA, PFAS, and any other PFAS that we might regulate in the future. And how do we assess that and ensure whatever is coming out of that pipe doesn't contaminate groundwater? So having more data on that and science on that. Standardizing analytical techniques for PFAS to reflect current technology is important, and the EPA is working on new methods. Also coming up with a common extended list of PFAS compounds that are based on frequency of detection in the environment is important. Using the most advanced analytical techniques, possibly isotope dilution, and then standardizing methods for solids and drinking water and monitoring wells is important. So as we make methods to make sure these different media types are addressed. And then there's emerging analytical tools that are being developed, such as the total oxidized precursor for PFAS techniques that are looking at sort of the mass of PFAS compounds and potential, the forming potential of certain PFAS compounds based on the overall mass of PFAS that's detected. Another area that could use improvement is PFAS reporting. As you probably gained from what I presented, is New Hampshire's trying really hard to figure out where these compounds have been used and released, but we don't have any clear mechanism for identifying it, so we have all these indirect ways of assessing where we might find this in the environment. But had it been included in toxic release inventory or a standard item list on the MSDS sheets, we would have a better way of tracking where we should be focusing our sampling efforts. Looking at the Clean Water Act is important. Developing guidance for surface water quality standards, both for fish consumption, dermal exposure, and impacts to aquatic organisms should also be listed on there. I'm getting more information about soil and biosolid standards to ensure that when we're looking at these things that we're protecting water quality and food safety. This could lead to new industrial pretreatment requirements, to get the PFAS out of the wastewater before it's discharged to the municipal system. And it could also impact the types of waste that wastewater plants accept. In New Hampshire, many of our landfills generate leachate from lined landfills, and this leachate goes to wastewater plants, and some of these wastewater plants produce solids that are turned into biosolids and land applied. And so really assessing if all these activities are compatible with the protection of groundwater at the end of the line is important. Another area is to look at occurrence of PFAS in our food. FDA has not integrated PFAS into its common market basket studies, and so getting better information on our exposure in foods is important. And also addressing PFOA and PFAS in imported products to make sure that we have a way of addressing the phase out of these products in general, so they're brought into our country, and some sort of checks on that to ensure they're not coming in, even if materials are labeled as not containing these compounds. Another area is looking at exposure pathways to PFAS other than drinking water and recommended mitigation measures. While we're regulating PFAS down to the part per trillion levels, and there's a lot of attention on addressing this in our drinking water at these really low levels, there's really no guidance or initiatives or any literature out there on telling how people can remove these compounds from their daily life, and how to get the stain-resistant carpeting out of your home, what types of clothing might be a risk. So really holistically looking at this issue and not just focusing on every last part per trillion in drinking water, but to assess all the exposure pathways, to provide guidance on how to reduce exposure if there is a health risk with these compounds. And then lastly, developing ways to give financial assistance to small community water systems and private well owners to sample for PFAS compounds. It can cost a few $100s per sample. They already need to sample for all of our important traditional contaminants that we need to keep an eye on and not lose our focus on making sure we meet those standards as well, but provide a mechanism where they could look for do testing on their sources and see if they have PFAS in their drinking water in addition to all the traditional contaminants. With that, I guess I have a few minutes. I'd be happy to answer some questions.